Okay. Before we start talking about some more current standard units of measurement, let's talk about some ancient measurements first. At one time, whether it was the king or some other ruler who was in charge, measurements were based on that person. So a foot would literally be how long a foot was, and a span would go from end of the thumb to end of the last finger. A hand, which would be thumb pressed up against the fingers, and that's still used to measure horses. Actually, how tall is a horse? It's a certain number of hands tall. A yard would be from the nose to the end of the fingertips, and we've standardized a yard to be 36 inches. We've standardized a foot to be 12 inches. I don't know how long a standard hand is for measuring horses. I probably should make a note of that. And then a cubit goes from the elbow to the end of your longest finger. And that's another ancient measurement that was used. Before things became standardized, and now we have 12 inches in a foot, 36 inches in a yard. Spans and cubits, I don't really think are used much anymore, and hands have a very specific use. But there were ways to measure things before everything got standardized. After it got standardized, it was a lot easier for people to communicate with measurements to each other. One of the things we're going to spend some time with is the metric system. Some of you may be fairly familiar with the metric system, some of you may not. If you are familiar with it, then a lot of this will be review. If you're not, then we'll go pretty patiently through this to try to make sure that we're all comfortable with what it is that we're seeing here. So one of the things that we would measure would be length. And our standard unit for measurement in metric for length is the meter. And a meter is approximately 1 yard. It's a little bit bigger than a yard. If you've seen a meter stick, it's a little bit longer than a yardstick. But that's sort of the standard unit of measure for length in the metric system is the meter. And then smaller than a meter would be a centimeter. And we'll talk more about these prefixes. Centi, a century has 100 years in it. There are 100 cents in a dollar. The prefix centi goes with 100. And a centimeter is 1/100th of a meter, which means there are 100 centimeters in 1 meter. When we go over and look at larger than a meter, now we're talking about further distances. A kilometer. Kilo, and like I said, we'll look at these prefixes in a minute, goes with the number of 1,000. And so there are 1,000 meters in 1 kilometer. And a kilometer is roughly 0.6 miles. So a little bit more than half a mile is a kilometer. As we go through these, if you have questions you want to ask, please feel free to just throw those out there. Up next, we'll talk about volume, which is how much stuff can fit inside something. And one of the ways volume is discussed is in terms of liquids, and the standard unit is a liter. And a liter is about 33 ounces. So it's pretty common for us to buy a 2-liter bottle of soda at the store, and a liter would be half of that, 33 ounces, roughly. A milliliter. Milli, this prefix milli, we might think that it would go with million, but it doesn't. It goes with 1,000. And there are 1,000 milliliters in 1 liter. Moving on to weight. When we talk about weight, our standard unit is the gram. And smaller than a gram, we would have a milligram, which just as before, milli corresponds to 1,000. So there'd be 1,000 milligrams in 1 gram. And just like before, kilo corresponds to 1,000 when it's bigger than the standard unit, and there'll be 1,000 grams in one. Oh, that should say kilogram. Sorry about that typo there. 1 kilogram. 1,000 grams in 1 kilogram. And just for a frame of reference, a kilogram is approximately 2.2 pounds. And so these are our basic metric units for length, volume, and weight. The standard unit that everything else is built around are the meter for length, the liter for volume, and the gram for weight, and then the prefixes get attached on there to go either smaller than the standard unit or larger than the standard unit. Those prefixes that I mentioned before. So if we talk about the base units, meters, grams, liters, that's our base unit. That's the sort of the standard thing. And then everything is based on that. And we either go smaller than that or bigger than that. We looked at centimeters. You could also have centigrams and centiliters. Those aren't used very often. Centimeters, certainly more common than the others. And cent, meaning 100, is where we get 1/100th. And then milli, when we talk about the millennium, that's 1,000-year period. And so while we might want to attach million to there, milli really goes with 1,000. And so a millimeter would be 1/1,000th of a meter. A milligram is 1/1,000th of a gram, and a milliliter is 1/1,000th of a liter. Deci is one that we don't use that often, but it does exist. I want to make sure you're aware of it. That would go with 10. And you can see the prefix in there. A decade is 10 years. And so deci leads us to tens. Then on the right-hand side of this, we go bigger than the base unit. Deca would be 10. So a decameter would be 10 meters. Deca and deci aren't really used that often. Same thing's kind of true with hecto for 100. We don't see that one very often. We don't see hectograms. But what we do see for each of these, especially meters and grams, is kilometers, which would be a kilometer is 1,000 meters. Kilograms, a kilogram would be 1,000 grams. And then a kiloliter would be 1,000 liters. I'm not really sure where that would come into play very much, but that's the prefix you would use. Let me know if you have questions about those before we move on from it. Okay. If the metric system is new to you, if you're not that comfortable with, meters, grams, and liters, here's some approximate measures just to sort of give you a frame of reference. The width of a standard doorway, that's about 1 meter wide. And, we talked about a meter being a little bit bigger than a yard, and so that helps too. But the width of a doorway is about 1 meter. And then the height of an average man is 177 centimeters, which we could write as 1.77 meters. Those would mean the same thing as each other, because remember, there's a relationship of 100 because of centi. So if we were to, multiply by 100, which would move the decimal point 2 places, we'd have 177 centimeters. And so the height of an average man, a little bit less than 2 meters tall. Now we get into weight or mass. The mass of a hardback textbook. It's about 2.2 pounds. So that's about 1 kilogram. And this is strictly just to kind of give you a frame of reference. You're going to see questions that sort of say, which one of these goes best with which one of these? Almost a matching type of thing. And so ideally, it'll be fairly obvious which one goes with which, as long as you have a general understanding of how much 1 kilogram weighs, how big a meter is, that kind of thing. The mass of a relatively thin adult would be about 60 kilograms. said a kilogram is 2.2 pounds, so somewhere around 120, 130, something like that. We haven't talked Celsius or Fahrenheit yet. We'll get there later today, but just to talk about metric temperature, it's measured in degrees on a Celsius scale, and temperature on a warm day would be about 27 degrees. Temperature on a snowy day would be -4 degrees. So, not as much range as we have in our Fahrenheit scale. Our Fahrenheit scale, a snowy day is probably somewhere in the 20s, and a warm day is in the 80s, maybe 90s. So these numbers stay closer together, and we'll see that when we talk more about Celsius and Fahrenheit in a little bit. And then as far as volume goes, down at the bottom here, we have a coffee cup holds about 1/4 liter, which would be about 8 ounces. And then just like we could kind of see with our meters and centimeters going back and forth, there'd be 1,000 milliliters in a liter. So if we were going to turn liters into milliliters, we'd multiply by 1,000. That's moving the decimal point 3 places. We'd land at 250 milliliters. That would be the same as 0.25 liters. If the metric system is new for you, you're not that familiar with it, you're not that comfortable with it, and this feels a little overwhelming, I don't think the questions you'll be asked will put too much strain on your knowledge. I want you to have a basic understanding of, well, meters are for length, and grams are for weight, and liters are for volume, and sort of just a basic idea that a kilogram is about a hardback textbook, and a meter is how wide a doorway is. And a liter is like half of one of those 2-liter bottles we buy at the store. It doesn't have to be encyclopedic knowledge. It just needs to be basic understanding of how big each of these things really are. I mentioned Celsius and Fahrenheit just a minute ago. Let's talk about those two temperature scales. So these are for measuring temperature. And in the Fahrenheit scale that we commonly use, water freezes at 32 degrees and it boils at 212. And I just kind of want to draw a little picture of that over here. So we have 212 is where water boils, and 32 is where water freezes. Now, water freezes and boils in the Celsius system also. And actually, the freezing point and boiling point of water is how the Celsius system got created. It was created with the idea in mind that, well, with Celsius, we're going to say that water freezes at 0 degrees, and I'm not going to do it that way. I'm going to draw a new. Water freezes down here at 0 degrees and boils up here at 100. And it was created based on the freezing and boiling temperature of water so that it could go from 0 to 100. Neither one of these is really better than the other. They're just different ways of measuring temperature. One thing I will say about them, though, is as we look at those two scales, from 32 to 212, there are 180 degrees in between freezing and boiling. In the Celsius scale, there are 100 degrees between freezing and boiling. So those are further apart. What that means is that, and we'll talk about this concept in a little bit, is that the Fahrenheit scale is able to be a little bit more precise because it has 180 degrees range from 32 to 212, as where Celsius only has 100, those are further apart. It's a little less precise. And the word precise we'll talk about in a little bit, I promise. If we want to go back and forth between Fahrenheit and Celsius, our formula is right here. Fahrenheit degrees is found by doing 9/5 times the Celsius temperature plus 32. For example, if it's 18 degrees Celsius, then what would the Fahrenheit temperature be? Well, let's see. Fahrenheit would be 9/5 times 18 degrees Celsius plus 32 degrees. And we just need to simplify that to be able to find Fahrenheit. I want you to be able to go back and forth between Fahrenheit and Celsius. This is the formula that we'll use. And let's see, nothing to do in parentheses. So now I'll multiply this order of operations. Parentheses, there aren't any exponents, so multiply is next. We're going to multiply here, and I'm multiplying a fraction, so I'm going to rewrite this whole number as a fraction. Now I'm going to multiply these. And let's see here. We will multiply numerators. 9 times 18 is 162. On the denominators, I have 5 times 1, that's 5, and I'll need to add 32. Well, let's go ahead and divide then. 162 divided by 5 is 32.4. So I have 32.4 plus 32, and I end up with 64.4 degrees. So if I'm given a question that says, it's 18 degrees Celsius outside, what would the temperature be in Fahrenheit? This is the process I would use. I would use this formula, plug in the Celsius degree that I know of 18 degrees right here, and then simplify by, there's no work to do in parentheses, there's no exponents, so we'll multiply, and we'll divide, and then we'll add. And a decimal answer is perfectly fine here rather than keeping it in the form of a fraction. And so we end up with 64.4 degrees Fahrenheit. Do you have questions on this before I have you try one that's similar? Okay, here goes. If the temperature is 86 degrees Fahrenheit, what would it be in Celsius? And just a reminder, that formula is that Fahrenheit is 9/5 times Celsius plus 32. This will require a little bit of algebra on your part, but I'm pretty confident. I'm gonna go ahead and set up a poll for you. I didn't give instructions on rounding, but you can see each of these has been rounded to the nearest 10th. So go ahead and do that when you solve this one. Round to the nearest 10th. So basically going back and forth between Celsius and Fahrenheit, we can go either direction. In the example we looked at last time, we knew the Celsius temperature and we had to find the Fahrenheit temperature. This time, we know the Fahrenheit temperature and we're looking for the Celsius temperature. Let's go another 20 seconds on this one, and then we'll talk about it together. All right, let's see where we are. Okay, spread around a little bit. So algebra review is a really good idea for us, I think. So we'll do a little bit of Fahrenheit and Celsius here, but also spend some time talking about the algebra that's involved in solving this particular problem. All right, so let's see. If the temperature is 86 degrees Fahrenheit, so we're going to plug 86 in for F because we know the Fahrenheit temperature, and we're looking for C, the Celsius temperature. So the first thing we have to do correctly is plug in correctly. We were given Fahrenheit, so we have to plug in for F. And now we'll solve this for C. All right, well, what I'm trying to do here is I'm trying to get C by itself. So I need to get the term that has c in it by itself. So as I look at the right-hand side of the equation, I need to peel this from the outside in. So the first thing I'm going to get rid of is that 32 by subtracting 32 from both sides. Those will cancel, and then I'll have whatever 86 minus 32 is. 54 is equal to 9/5 times c. Now I have 9/5 times c. I want to make that 9/5 go away. And this is something we've done before, and some of you actually knew exactly what to do here. If I want 5/9 to go away, I'm going to multiply by the reciprocal. I mean, if I want 9/5 to go away, I'm going to multiply by the reciprocal. I'm going to multiply by 5/9 because that's going to get the 5s to cancel and the 9s to cancel, leaving me just the c. If we multiply by 5/9 on the right-hand side, we also have to multiply by 5/9 on the left-hand side. It may be more comfortable when multiplying something that involves a fraction to go ahead and rewrite the other number as a fraction. That whole number we can rewrite as a fraction also. And now we'll just multiply. I don't know what 5 times 54 is, but those are my numerators, 270. 9 times 1 on the bottom is 9. And so finally, 270 divided by 9 gives me 30 for my Celsius temperature. We have to plug in 86 for Fahrenheit and then be careful in our solving process. Subtract 32 from both sides, multiply both sides by 5/9, and then finally do 270 divided by 9. Let me know if you have any questions on what we did there. Got it. Okay. Those are easy things to fix, Jennifer. It's nice when you can see those kind of things. Like, I totally understood what was happening. I just made a mistake when I typed in the numbers on my calculator. Those mistakes can be frustrating, but they indicate that you didn't know what to do. And that's the most important thing, because simple mistakes like that happen from time to time, but they're not that hard for us to avoid. Easier to fix that than I really have no idea what's happening in solving the equation. That would take a little more effort. Any other questions on this before we move on from it? Okay. The metric system gained popularity. You know, everything's based on tens. There's, 100 centimeters in a meter. There are 1,000 grams in a kilogram, versus the system of measurements that we tend to use can be a little goofy. I mean, 12 inches in a foot, 3 feet in a yard, it's not, as well organized as the metric system. And given that it was gaining popularity, the idea of metric time got proposed at one point, where there would be 10 hours in a day. Now, this sounds crazy. How can you only have 10 hours in a day? Well, an hour would be longer. An hour would be about 2.5 times as long as it is now, would be an hour, because there would be 10 of them to fit in the day, the time it would take for the sun to go down and come back up for us. There would be 10 days in a week. So we would have these 10-hour days, and we'd have 10 days in a week, and then we'd have 10 months in a year, trying to base everything on 10. Well, as you may have guessed, this didn't fly. We don't use metric time. It was proposed. I think it's a wild idea that, that could even get suggested, but no, it didn't happen. And well, I personally am kind of relieved. Okay. I mentioned the word precise earlier today. And right now we're going to talk about the difference between accuracy and precision. Accuracy is how close the measurement is to the true measure. Like, how close is my measurement to the truth? And then precision is kind of more based on the instrument you're using to do your measurement. How exact is the measurement? How exact are you? What kind of a tool did you use to measure this? Did you use a yardstick and find it in inches, or did you use cubits going from your elbow to your fingertip? One of those is going to be more precise than the other. Here's an example. If we look at my height, and I'm roughly 6 feet tall, a little bit under, but roughly 6 feet tall. If we were to say that I was 48.3165 inches tall, that is extremely precise. I mean, heck, it goes to the 10,000ths place. It's really precise. Whatever you use to measure that had a very high degree of precision, because look at all those decimal places. The problem is it's not accurate, because 48 inches is nowhere close to how tall I am. When you think about the fact that, well, if you're 6 feet tall, that's 72 inches. This isn't even close. So it's not accurate because it's not close to the true measure. It's precise because whatever you used was able to go to the 10,000ths place, but it's not very accurate. Then in contrast to that, if you were just to ballpark it and say, yeah, 6 feet, well, that's reasonably accurate, but it's not very precise because it just 6 feet. It's not even to the nearest inch. It's just, yeah, 6 feet, close enough. And it is relatively accurate, but it's not very precise because it's more of a, it's close. But we can't say with any more degree of certainty better than that. Whatever we're measuring with only has feet on it. Doesn't even have inches. So we're not very precise. Let me know if you have questions on the difference between those two. Okay, very good. And one other thing I did want to say about, with precision, kind of depends on the tool you're using to measure. We might be able to get just to the nearest inch, but depending on what we're measuring with, we might be able to get to the nearest half inch. That would be more precise. We might be able to get to the nearest 1/16 of an inch, which would be really precise. And so that's kind of how we describe precision, is how exact can you be based on what you're measuring with. Percent error. We talked about accuracy being, well, how close is it to the real thing? We have a way of deciding that, how close it is to the real thing. And the way that we do that is with what's called percent error. And percent error is found with a formula. And that's the amount of error divided by the actual amount. So whatever the actual amount is going to be on the bottom. That's our, that's the true number. And basically what we're saying is, how far away from the actual amount is your measurement? This is going to give us a decimal number. Because we're talking about something that is percent error, we're going to convert that decimal to a percent when we're done. Let's look at an example of this. A 6 foot tall man is measured to be 10 feet tall. A 76 foot tall building is measured to be 80 feet tall. Which of these has a higher percent error? I'm going to do the first one, then I'm going to set up a poll to have you answer this question. But I'm going to do the first one first. So the first one, a 6 foot tall man is measured to be 10 feet tall. So our percent error here is going to be, well, the amount of error. You could do this strictly by looking at it and say, well, he's measured to be 10, he's actually 6, so it's off by 4. If you want to do it that way, that's fine, but a lot of students are more comfortable just writing that down. What is the difference? Subtract between the actual measurement and the measurement that we received. So if we do 10 minus 6, and then here's the only place you might make a mistake in a percent error calculation. The number that goes out on the bottom is the actual amount. So we want to make sure that if he's 6 feet tall, that's the number that goes in the bottom. So the percent error for measuring this man, well, the amount of error is 4. The actual height is 6 feet. We'll divide that, 4 divided by 6, and get 0.6666. That keeps going. I didn't put where to round on here. Let's go to the nearest hundredth, and then we'll have a whole number answer. So if we go ahead and convert this decimal to a percent, we'll move it over 2 places. We're at 66.6666%. Now we'll round to the hundredth. Sorry about that. I misspoke a minute ago. Now we'll round this to the nearest hundredth and say, all right, 100th place, look one space to the right. That's 5 or bigger. So the percent error for measuring this man is 66.67%. Let me know if you have questions on what I did there to find that percent error. And if we are all good, what I want you to do is now answer this question: which of these has a higher percent error? And I'll make a poll for it. So we found the percent error for the man. Your job is to find the percent error for the building and then decide which one has the higher percent error. Let's go another 20 seconds and then we'll talk about it. If you need more time, let me know. All right, let's see where we are on this one. Unanimous. Fantastic. That's really good. I was hoping this would go that way, and it did. Let's go ahead and take a look at this one then. Doing the calculation for finding the percent error on the building, just as a way to review that idea again. So for the building, our percent error is going to be, let's see, percent error for the building will be, all right, let's see, how far off is it? Well, it's measured to be 80, but it's actually 76. So I need the difference between those. And the number that goes on the bottom is the actual amount, which is the 76. Be careful there when you're doing percent error. So we wind up with 4 over 76. And we'll do that division. 4 divided by 76, and I get, let's see, 0.052631, and that keeps going. I want to convert that to a percent. So I'll move the decimal over 2 places, and I'll have 5.2631%. If we round that to the nearest hundredth, let's see, hundredths place, look one space to the right, that's 4 lower, so we'll round this down to 5.26%. So the percent error on the building was 5.26%. If you were just asked for percent error, that's what we're looking for. This question said which one has a higher percent error? Well, the building's percent error is 5.26%. The man's percent error was 66.67%. So the man definitely had a higher percent error. Basically, what we're saying is, how far off is your measurement? And it's one easy mistake to make here is to look at these and say, well, 6 foot tall man, 10 feet, it's off by 4. 76 foot tall building, 80 feet, it's off by 4. They're the same. Well, as would probably make logical sense to you, if we measure a 6 foot tall man to be 10 feet tall, we're not even close. If we measure a 76-foot tall building to be 80 feet tall, that's not terrible. It's only off by 5%. So clearly, the measurement of the man had more error, and that's what percent error can tell us. Poll went great, but if you have any questions, let me know. Okay. Dimensional analysis is something we're going to cover today. This is something you may have seen in a science class, especially a chemistry class, somewhere along the way. And what we're going to do with dimensional analysis is we're going to be given a measurement in one unit and convert it to a different kind of unit. The way we're going to do that is through the use of what are called unit fractions. And a unit fraction is something like this: 1 mile over 5,280 feet. It's called a unit fraction because technically it's equal to 1, because the numerator and the denominator are the same as each other. 1 mile is the same as 5,280 feet. And anytime we have a fraction that has a numerator and denominator that are the same as each other, it's equal to 1, which is the primary unit of counting. And so that would be a unit fraction. Numerator and denominator are equal to each other. Other examples would be 12 inches is the same as 1 foot. Numerator and denominator are equal to each other. That's a unit fraction. Something that might take us from English units to metric units is 1 inch is the same as 2.54 centimeters. Here again, numerator and denominator are equal to each other. Those are all unit fractions. We're going to use these to do conversions. And here's how that goes. A recipe calls for 250 milliliters of milk. How many liters is this? So what we want to do here is we want to take 250 milliliters and turn that into liters. That's what we're trying to do here. The thing that we're converting, the thing that we're starting with, the 250 milliliters, we're just going to write that down. Some students don't like this scaffolding. If you don't have to use it. You can write these as fractions instead. I'm going to use the scaffolding sometimes and then other times not, just so you can see it both ways. The scaffolding is essentially just creating a fraction right here that has a numerator and a denominator, but there's nothing in the denominator. We're just using 250 milliliters of milk. I want to convert this into liters. And so what I'm going to do is I'm going to set up a unit fraction right here that is, let's see, well, I know that there are 1,000 milliliters is the same as 1 liter. And then I'm going to just kind of get an idea of how comfortable you might be with this topic already. What I'm going to do is I'm going to create a unit fraction using this information right here, 1,000 milliliters and 1 liter. One of those is going to go in the numerator. One of those is going to go in the denominator. My question to you is, and this is basically just me fishing a little bit to see how comfortable you might be, how much experience you might have with dimensional analysis. If nobody knows, it's totally fine. My question is, which one is going to go up here in the numerator? The 1,000 milliliters or the 1 liter? Which one goes in the numerator? If you don't know, it's totally fine. Okay, Sunshine says 1 liter goes in the numerator. Agreed. Very good, Brianna. That's excellent. And honestly, and Summer too. Perfect. This is good. This is the hardest. Very good, Nadine. Excellent. This is the hardest thing about these problems is, okay, so I've got this unit fraction here. Now I've got to figure out how to put it in there. And the 1 liter is going to go on top, not just because a liter is bigger or anything like that. It's because we want the 1,000 milliliters on the bottom, because what our goal is with this whole unit fraction is to make milliliters cancel. And so I need to put milliliters on the bottom because now I have milliliters on top of a fraction. Over here, I have milliliters on the bottom of a fraction, so they'll cancel. Now, when I look at my units that I have remaining here, the units that I have remaining are just liters. That's it. The only units I have left are liters. The problem told me to turn it into liters. So that's it. Once I get to this point where I have the units that I want, now I will multiply numerators together. 250 times 1 is 250 liters. And multiply everything on the denominator. That's just 1,000. There are no units down there. And the last thing I'll do is divide 250 divided by 1,000, and I get 0.25. And that is how many liters 250 milliliters would be. This is an extremely simple example of dimensional analysis. We will ramp up the degree of difficulty as we look at future examples here, but at its core, this is what we're doing. We're given some value that we need to convert. We're going to use a unit fraction to convert it. And by converting it, we're just getting those units to cancel each other out. Let me know if you have questions before we look at another. Okay. Use the fact that 1 inch equals 2.54 centimeters to convert 40 inches to meters. Round your answer to the nearest thousandth. All right. Sometimes a student will read this problem and have no idea where to start, but don't overthink it. This says right here, convert 40 inches to meters. So what I'm starting with is 40 inches. So I'll put my 40 inches in, and we'll do this one with the scaffolding. All right, I'm starting with 40 inches. I want to turn that into meters. So by the time this is all done, I need to be in terms of meters. Well, I was given this unit fraction right here that says 1 inch is 2.54 centimeters. That's going to get me from inches to centimeters. It's not going to take me all the way from inches to meters. I can't do that in one step here, but that's okay. I've got one step in the right direction by using this unit fraction right here. Just like we did in the last one, I want stuff to cancel. So I'm going to put my 1 inch in the bottom and my 2.54 centimeters on the top. And that's not random and it's not a guess. The reason I did that is I want to use this unit fraction to get inches to cancel. So I had to put the inches on the bottom, so the centimeters went on top. Okay, well, I started with inches, now I have centimeters. I'm not quite done though, because I need to get to meters. And I remember, oh yeah, so there are 100 centimeters in 1 meter. So I need another unit fraction here. Okay, well, do another unit fraction. And that unit fraction will be, let's see, I've got 100 centimeters in 1 meter. Where do I want to put the centimeters? On the top or on the bottom? Do I put my centimeters on the top of this or on the bottom of this? And I think everybody knows, I'm just making sure. Outstanding. You're going to do great with this topic. Okay, so I put my 100 centimeters on the bottom and my 1 meter on the top. Again, it's not a guess. It's not, I hope I put it in the right place. It's, I have centimeters on top that I want to cancel. So the centimeters in my unit fraction need to go on the bottom. And now I can look at this and see, hey, the units that I have left are meters. I was trying to get to meters. So I'm done. I don't need any more steps. That's it. I went from inches to centimeters, now to meters. Now I don't need to do any more unit conversions. I don't need any more unit fractions. I'm going to multiply everything I have left on the top, multiply everything I have left on the bottom. When I multiply on the top, I have 40 times 2.54 times 1, and I get 101.6. And I have meters, so I'll keep those. On the bottom, I have 1 times 100, and that's just 100. I don't have any units down there, so it's just 100. And then the last thing I'll do is go ahead and divide by 100, and I get 1.016 meters. So if I want to convert 40 inches into meters, 40 inches is going to be the same thing as 1.016 meters. Let me know if you have questions on that before I have you try one. Excellent. Here goes. Use the fact that 1 kilogram is 2.2 pounds to convert pounds to grams. And just to throw you a bone, in case you're not that familiar with the metric system, I am going to go ahead and give you this one, that there are 1,000 grams in 1 kilogram. All right, I'll set up a poll for this, and I'll let you try it. So the idea here is start with 165 pounds, use however many unit fractions you need to turn those pounds into grams. Let's go another 20 seconds and then we'll talk about it. If you need more time, you let me know. Dimensional analysis is a concept that can be challenging for students sometimes. I think this is one of those light bulb comes on kind of topics where it's like, oh, now I totally understand what to do. And until you get there, they can be hard, but once you get there, you'll never get one wrong. So I want to help you get to that place if you're not there already. All right, let's see how we did on this one. Not unanimous, but close. All right, let's talk through it. If you see something that you're not sure why it happened or, why that particular thing went in that particular place, make sure you ask about it. I've done the others with the scaffolding. This one I'm going to do it without, just in case. Some people find that scaffolding to be sort of off-putting or intimidating or something, so we'll do this one without it. So I'm starting with 165 pounds that I want to convert to grams. So 165 pounds. And I'm going to multiply this by a unit fraction. Let's see. I've been given two unit fractions up here. I've been given this one that says there's 1,000 grams in a kilogram, and this one that says kilograms and pounds. Pounds is the thing that I have, so I need to use the unit fraction that has pounds in it. This is kilograms and pounds. I have 165 pounds. I'm going to want to put my 2.2 pounds on the bottom because I need pounds to cancel. So the 1 kilogram goes on top. So I started with pounds. My pounds have canceled, so now I have kilograms. Well, I'm closer, but I'm not there yet because I'm trying to get to grams. Now I'm going to use my other unit fraction, and I'm going to say, all right, then I'm going to multiply by this other unit fraction that has grams and kilograms. I want kilograms to go away, so I'm going to put that 1 kilogram on the bottom and my 1,000 grams on the top. Once I do that, I can see that the kilograms cancel. And now I have grams. That's what I was trying to get to. So I don't need any more unit fractions because I've reached the point where I have the unit that I'm after, grams. So we'll multiply everything on top, multiply everything on the bottom, and then we'll divide to get our answer. 165 times 1 times 1,000, that'll be 165,000, and that's grams. On the bottom, 2.2 times 1, 2.2. And the last thing I'll do is divide. 165,000 divided by 2.2, 75,000 grams. So if somebody weighs 165 pounds, they weigh 75,000 grams. Let me know if you have any questions on that one. That's sort of our dimensional analysis type of problem and approach. We did it with the scaffolding and we did it without the scaffolding. It's the same, it's just which way do you prefer to write it down. I do want to look at one more. Use the fact that there are 5,280 feet in 1 mile to convert 38 miles per hour to feet per second. All right, well, it says convert 38 miles per hour. Wait a minute, I have this word per in here that I haven't seen before. That's going to increase our degree of difficulty here. When I have my 38 miles per hour, that's 38 miles per every 1 hour. And what's different about this problem from the others is I have something in the denominator when I start. That's okay. I'm starting out with miles per hour, and the problem tells me that my answer is supposed to be in feet per second. So what I'm going to have to do over the course of this problem is turn these miles into feet and turn these hours into seconds. I'm going to want to finish with feet in the numerator and seconds in the denominator. So the process is going to be exactly the same. It's just going to be a little bit more involved because there's two things I have to convert: miles to feet and hours to seconds. Well, I've got this unit fraction right here, 5,280 feet in 1 mile. I want miles to cancel, so I'm going to put my 1 mile on the bottom and my 5,280 feet on the top. Miles are going to cancel, and at this point, if I were to quit right now, what I have is feet per hour. Well, the question said get feet per second. So I'm not done yet, but I am closer. At least I have the feet part down. Now I need to turn hours into seconds. And I don't know about you, but I have no idea how many hours are in a second, or how many seconds are in an hour. But I do know that there are 60 minutes in 1 hour. Okay, let's see if I can use that then. 60 minutes for 1 hour. I've got an hour on the bottom. I want that to cancel, so I'm going to put my 1 hour on the top and my 60 minutes on the bottom. Okay, let's see what that does for me. That gets these hours to cancel. If I were to quit right now, the units that I have are feet per minute. Well, it's still not feet per second, but I'm closer. I'm getting there. I started out at miles per hour. Now I'm at feet per minute. Okay, so I need to turn those minutes into seconds. One more step ought to do it. So let's see here. I know there are 60 seconds in 1 minute. So let's see, my unit fraction here will be, I've got minutes on the bottom that I need to get rid of. So I'm going to put that 1 minute on top and my 60 seconds on the bottom. At this point, my minutes cancel. And what are my units now? Feet per second. Hey, how about that? I made it to feet per second. I don't need any more unit fractions. I'm good here. Now I'm at that place where I can multiply everything along the top, multiply everything along the bottom, and then when I get to the end of that is when I get to divide. And let's see, across the top, I've got 38 times 5,280 times 1 times 1. Big, ugly number, but it's not my answer. 200,640, and that is miles. On the bottom, I have 1 times 1 times 60 times 60. That's 3,600. And I do have a unit down there. I have seconds. Oops, and it's not miles on the top. Sorry about that. It's feet on top. There we go, feet. So I have feet per second, and the last thing I'll need to do here is divide them. 200,640 divided by 3,600, and I end up with 55.733333 feet per second. This one actually told me where to round. This said round to the nearest tenth. So we'll find the tenth place, look one space to the right, and we'll round this to 55.7 feet per second. So if you happen to be driving 38 miles per hour, you are traveling about 56 feet per second. That is a challenging problem because we not only had to convert miles to feet, we also had to convert hours to seconds. If that made sense and you were comfortable with everything that happened there, then you're in really great shape with dimensional analysis. Are there any questions about what we did in that one? Outstanding. Okay. Last thing that I want to say is about homework number 24. When you first read number 24, it reads pretty difficult, but honestly, I'll just tell you right out, it's not as difficult as it first appears. Use your problem-solving skills. Don't think about, don't think about dimensional analysis. Don't think about the metric system. Don't think about formulas. Think it through, reason it out, use your problem-solving skills to think about how you would come up with the answer for that one. And I'll just